Swayam Prabha. Digital India. Educated India.
Good morning. So we were looking at a few examples of jump Markov process modeled using chemical master equations. I think we looked at a couple of examples already. One is in irreversible first order reaction and one-sided random walk Poisson process and so on. And I think we also looked at one example of a chemical that is photolysis of a molecule where Poisson distribution is useful to interpret the data of fluorescence intensity decay. Now we want to continue on that. Now I want to give some extra problems so that we kind of get more experience of how to use chemical master equation to model more such problems. In this context, I want to discuss two problems today. One is a regular random walk, the bidirectional. Okay, so last time we talked about only one directional. So here we will talk about the one dimensional random walk where the particle can move both in the positive as well as negative direction. And then we also extend this chemical reaction to a reversible reaction. Okay, what we saw before was irreversible reaction. Now we look at reversible reaction also. We are looking at these problems because these are all analytically solvable problems. Okay, and once we are comfortable with how we use this chemical master equation, how to set it up, and then when there is a more complex reaction networks, we know how to set up the chemical master equation. Then we worry about whether this will be solved analytically or numerically and so on. Okay, so we are kind of practicing how to make use of master equation for more such problems. So the first problem we want to do here is one dimensional random walk. We have already discussed enough about Brownian motion and random walk, and then it is a Markov process. So if you remember, we looked at this problem previously in the context of Langevin equation. Okay, so the Langevin formulation predicted. So Langevin prediction is that the mean position is 0 and the mean square displacement was this was proportional to t or sometimes like 2 dt or something like that. Okay, so mean square displacement increases linearly with time. Okay, see, these were the predictions from Langevin approach. And the Einstein's approach, I showed the solution but I did not give the details yet, but this tells you that the position, the probability for finding the position at time t of a Brownian particle is Gaussian distributed. Okay, so these are the known results. We have already seen Langevin equation. We set up the Langevin equation and looked at the mean and mean square displacement, and we derived these results. And then in the case of Einstein formulation or a continuous Markov process approach, which we are yet to discuss, and the solution will for this problem be a Gaussian distribution. Okay, in all these cases, this d here denotes the diffusion coefficient or the diffusivity of the Brownian particle. Okay, so these things we know. So now we want to relook at this problem, same problem, but more from a discrete point of view. Okay, because master equation is used for discrete or jump processes. So if you want to convert this problem into a jump Markov process, what we need to do is we take the spatial domain, okay, and the spatial domain is a continuous domain, and we try to discretize this. Imagine that you have a lattice and the particles can only take those well defined lattice position and nothing in between. So then we are saying that there is a lattice point here, another one here, they are all equidistant Okay, so we say that this is 0, lattice position at 1, 2, 3, 4 and so on, so, and similarly it can go in the opposite direction, so -1, -2, -3. So therefore we can discretize the space into a lattice positioning, and then we imagine the particle, the Brownian particle which starts at somewhere here, can either go here or here. Okay, so it takes a unit step jump. Okay, so we are saying that the step length is some unit distance. Okay, so therefore we already know that this is a Markov process. Now we are saying that by discretizing the spatial variable, we say it is a jump Markov process. And what we hope to do is, for now that we have a jump Markov process, we should be able to write down master equation for this problem, and then when we solve them, we should be able to get these results. Okay, because the same problem can be analyzed in various framework. Okay, we are talking about 3 different framework. One is the Langevin framework, master equation framework, and the continuous Markov process, which is the science and approach, or later on I will introduce this as a Fokker-Plunk equation. So this is something we will see after the discrete Markov process is discussed. So, in this case we will write the chemical master equation. So this is our master equation for a discrete case, and now for this problem we want to write this equation. So if you look at the way that we discuss think about this problem is that a particle can be at any position at some place x, and then it can go to either x plus 1 or x minus 1. So I think what I'll do is I will probably change the variable into x, because we are talking about position. Yeah, this is also x. This is also x. So we have kind of this 2 possibilities, that x, when it is x, it can go to x plus 1, or being in x, it can also go to x minus 1. Right? These are the 2 possibilities. When the particle is at position x, the next jump it can go to x plus 1 or it can go to x minus 1. So what that means is that now m can take a value of x plus 1 or it can take x minus 1. These are the 2 possible values of m. You cannot go to x plus 2 and you cannot go to x minus 2. Those jumps are not relevant. Okay, so now we can write this equation for 2 values of m. So first let's write this for m x plus 1. So here we'll have So when you substitute m is equal to x plus 1 in here, you will get these two terms. Then we have this m is equal to x minus 1. So now we have to deal with these rate constants, right? We need to define this. What can we say about this? At time t, the position is at x plus 1 and the rate at which it will jump to x plus 1 to x. Okay, what would that be? We can associate some constant. Okay, we define some rate at which that rate will depend on the diffusion coefficient and temperature and everything. Okay, so we'll say this is some value a, and this a, look at this a rate constant does not depend on the time and it doesn't depend on the current position. Okay, we define the jump rate is constant regardless of where the particle is and what time the particle is found there. Okay, so we associate this as a some constant value. The second one, so at x comma, so at time t the position is at x and it is making a forward jump. What would this be? What would this be? So this is like jumping backwards, this is jumping forward. So what would this be? 1 by s, 1 minus a. Okay, that's fine. If you do this, what you are inducing here, if you say 1 minus, that's a valid definition, but by doing this, what are you doing? Suppose if you take a equal to 0.1, then 1 minus is 0.9, then you are biasing the two jumps. You are favoring one side of the jump more often than the other one. But we know that for a Brownian motion, one dimensional random walk, the probability to jump forward and backward are equal. Okay, so that means if this is a and this also has to be a. Okay, so because we are not biasing, there are biased random walks too. In that case, we can define two different variables. You can put a there and b here, and then we can. Okay, but now we are talking about an unbiased free Brownian particle which will have equal probability to go forward and backward. So all of them are actually a. So this becomes some constant a. This also becomes just a. So in other words, we are saying that dp by dt of position x comma t is a times p of x plus 1 t plus a times p of x minus 1 t minus 2a p of x comma t. You see, if you look at the rate of increase of probability of state x, it can increase if the jump happens from x plus 1 backwards or another jump which is forward from x minus 1 to x. So these are creation of the probability state. But being in this, it can also go to here or it can also go to here. So this will be loss of probability and this will be generation of probability. These two arrows corresponds to the first two terms. The last terms are this 2 times A P of x comma t. Okay. Without going through the chemical master equation, identifying M, one can also write this more intuitively by looking at this kind of jump process. But it's probably a good idea to start with the governing equation and then look at what are the possible states and then write the probability rate for each of those states, and then you come to this so that we don't make any mistake. Once you get used to this for more often, you don't have to kind of go through this. You can directly also write this equation by looking at what are the possible state change processes. Okay, so you can always try to draw this kind of a diagram or a schematic marking where x is, what are the possible events. Okay, look, we are not looking at x going to x plus 2, this is forbidden. X minus 2 also forbidden. Okay, but there may be some if you want to do a project, if you want to do some more complicated Brownian motion, there could be other deviations from this model, that you may have non-biased, you may have a biased random walk because there may be a potential acting on this particle that it prefers to go in one direction more often than the other, or you may want to say that the step change can be also not a unit distance. You can have super diffusive behavior where once in a while the step can be 2 times the unit length. A lot of variations is possible depending upon what process that we want to model. Okay, but it's very important to understand this very basic level theory, and then you can always adapt and modify to different situations. Yes. Yeah. Now, A is not the probability, it is the rate constant, it's a probability per unit time. So the sum of this constant need not be always 1. Okay, so when we talk about a random walk, we usually remove the time constant, we just say probability to move back and forward. But here we are actually looking at from this time domain also, we are looking at the stochastic process. So here we define this as a rate constant. What is the rate of change of probability per unit time? So therefore these A's need not add up to 1 because these are rates, the rate of change of probability per unit time. Okay, this has to be distinguished from the other domain where we think about the probability jump is A and probability not to jump is 1 minus A and they add up. Okay, that is also okay, but those are discussed in the context of time independent processes. Okay, so here we define A as not as a probability but rate of change of probability per unit time. It's like a rate constant. Okay, so there is a difference. In the previous two problems, I discussed how to handle this kind of a recursive differential equations. We generally define a generating function, change the variable from x to some other variable s, solve in the s domain, and then you recreate the the probability distribution function p of n comma t. Or you don't have to necessarily solve the probability distribution function p of n comma t. If you get the equation for g, the generating function, we can take the derivative, first derivative, second derivative, calculate the derivative at s is equal to 1, and those are related to mean and standard deviation. Okay, so now I want to skip those steps because it's something that we have discussed already, and I will share in my notes the details of this process, but for the class we will directly write the equations, a solution for these equations using generating functions. So we say the generating function g of s comma t is defined as okay. So we have this definition of generating function, and then you apply that to this equation. Okay, so then you will get a differential equation. So if you map this master equation with this generating function, you will get a differential equation for G, okay. And then when you integrate this and use the initial condition, that is initial condition being that at time t equal to 0 the position is origin, you will get the analytical solution for G, okay. So from here you can rewrite this equation in terms of a sum series, match the coefficients and get P of x comma t, that is one way. Or you can take this, take the first derivative, second derivative, estimate the mean and standard deviation also, okay. So you will get that if you take the first derivative and calculate at s equal to 1, you will see that the mean position is 0 as we expect, and then if you get the mean square displacement or the mean square position, it actually goes proportional to t, okay. So these are the results we already expected from Langevin equation and the Einstein relation also. Also note that this unit of A here is 1 by time, okay. So then this mean square displacement looks non-dimensional. This is because we took the spatial unit length as 1, okay. If you have some other measure for that, then it should be meter square, this should be meter square by time, okay, but we have taken unit step length, so it becomes 1 by time. So this looks non-dimensional because it is based on the unit step size, but more importantly it is proportional to time, that is more important result. So now let us look at the other other system, that is a reversible chemical reaction, and then we follow this. So Kf here is the forward rate constant. The rate constant for the forward reaction, and Kb is the rate constant for the backward reaction. Okay, so first of all we have to define what is the random variable that will describe this process, okay, and that random variable will have Na and Nb, okay. If you think about a batch reactor and you start with some number of A and B or just only A, and then at some time t you want to describe what is there in the system, and to do that you need number of molecules of A and number of molecules of B, okay. There are two variables that you have to define to fully describe what is the content of the reactor. But in the reaction chemistry, stoichiometry, we know that for every one molecule A decaying, one molecule of B is created. So that means we know that the total number of molecules have to be preserved, and we know that whenever A changes, how B will change, and when B changes, how A will change, okay. These are kind of correlated changes. So therefore, we do not necessarily need two random variables, we can just work with only one random variable and use mass balance to get the number of molecules of the other kind. Okay. So we can say that instead of looking at two variable problem, we can think of our random variable is only Na, because at any point Nb will be N0 minus Na. We placed this argument before for the case of irreversible reaction also. Okay. So therefore we want to deal with only one rate constant, and in fact we will replace Na and just keep it as N, and we think that Na means Na. Okay. Number of molecules N means Na, and once I know Na I can find Nb, so we have only one random variable. Okay. So we have defined the state variable is just only number of molecules of A. The second thing is we have to justify it as a Markov process and it is a jump Markov process. So even though there are two reactions, okay, so A can react to B and B can decompose back to A. Okay, there are two reaction channels. We would like to think about a time scale where at any given time interval there is only one reaction that is possible. Either you can see a forward reaction or a backward reaction. If the time window is too big, you may see many forward reactions and many backward reactions. Okay, so we are not thinking about that. We are thinking about some time scale where there is only a likelihood of one reaction happening, that can be either a forward reaction or a backward reaction. So if I look at this time domain, then I can justify that this process will depend on only the current state, and therefore it is a Markov process. The second is, when this molecule is reacting, we also say that the number of molecules will change by 1, because it can either increase or it can decrease. So we say it is a jump process. Okay, because the state variable here is a discrete variable. The numbers are not continuous, numbers are integers here. So the number can only change by unit 1 plus or 1 minus. Okay, so we say that this reaction is looked upon at a particular time scale where at any given time only one reaction can happen, and that's true. It can change by number, by unit. It can increase the number by 1 or it can decrease the number by 1. Okay, so we have to place all these discussions to justify before you apply a master equation. So this is our master equation. So now here we will think about this reaction being, now we want to know what are the possible values of M. So we will think about this as first the forward reaction. So in the forward reaction, we can have M as you can have from forward reaction can only take it from n to n minus 1 or n plus 1 to n. Okay, so these are the possibilities. If there are n molecules at time t, any forward reaction can take this molecules to n minus 1. Okay, this is one possible M value. Or if the current state is at n plus 1, one forward reaction can take it to M also. Okay, so these are the process that will change state n. N can be that the property can be destroyed or it can be created. This is by only by the forward reaction alone. Yeah. The current states are different, right? So here the current state is n. The probability of finding the current state at n is different from the probability of finding the current state at n plus 1. So they are not the same. So by sort of indexing, you can say they are the same thing, but this rate depends on how many number of molecules are there at n. Because I am looking at rate of change of n, I am looking at all the process that will affect this. This process will affect will be affected negatively, this process is affected positively, right? Because this is getting created. So we are looking at many intermediate states. So remember, I have showing this diagram, right? So if I have state n, I want to know by forward reaction how the state n will be affected. That does not mean I have to only look at an n and see what happens to n. I have to look at the neighborhood, whether something is getting created also. So since it's a forward reaction, which means A can only decay, then I am asking what are the process by which the state n will be affected. I see there are two possibilities. One is it can either jump to n minus 1, sorry, n minus 1 is this way, it cannot go to n plus 1, okay. Forward reaction does not increase number of A, only the backward reaction will do. So for forward reaction, this jump is not possible. So you have to look at only this, n to n minus 1, that is this, okay. But there is a process, a state may be at n plus 1 and it can go to n, that is a creation, okay. When we talked about this random, the previous problem, random jump, we looked at n and see what are the process that affects the n itself. It can be jumping away or jumping to, all that has to be discussed, and that should be summed over. That's the meaning of this equation. So we would like to basically use m is equal to n minus 1 and m is equal to n in these equations. And this is only for forward. Similarly, we have to write for the backward also. So in the backward reaction, what happens? You can have n minus 1. If I have n minus 1, one backward reaction can take it to n, and then if I have n, it can go to n plus 1, right? So in the backward reaction, if I look at the processes that affect the state of n, is one of them is this that you know, you can have n minus 1 A molecule, one backward reaction will put one more A, so that becomes n, okay. So now when the system is currently at n, one backward reaction will put one more molecule, will become n plus 1. So this is creating, this is destroying, just like how we found in the forward reaction. Similarly for the backward reaction also this happens, okay. So now we first identify these processes, okay. Now we can use for m is equal to n minus 1 n, and similarly for this, and then we will write the corresponding rates. So W n minus 1 given n, what would this be? Forward reaction given n, it becomes n minus 1. So what would this be? K, Kf n. Okay, what about here? W n plus 1. What about this? Forward reaction with the state n plus 1, what the rate would be? Kf times n plus 1, correct, right? Now here we are talking about backward reaction. Wn n minus 1, what would this be? Kb rate constant is correct, and you are saying n minus 1. What is n minus 1? N minus 1 is the number of molecules of A. The backward reaction, does it depend on the number of A molecule or number of B molecule? Number of B molecule. So if number of molecules of A is n minus 1, what would be Nb? So note that Nb is equal to N naught minus Na, okay. Now I am interested in, if number of molecules of A is n minus 1, what would be the number of molecules of Nb? So that would be N0 minus n minus 1. So this is n naught minus n plus 1. This would be the number of molecules of B, and the rate is proportional to Kb times this number, not this number, because the backward reaction depends on the number of B molecule, not the A molecule. So this is not correct. So it should be n naught minus n plus 1. Okay, do you follow? Okay, similarly let us write this W n plus 1 n comma t Kb n naught minus n. So the backward reaction going from n to n plus 1 depends on the rate constant Kb. When there is number of molecules of A is n, number of molecules of B is n naught minus n. Okay. So having defined all these rate constants, now we can substitute that here, and then we'll get the master equation for this. This should be n plus 1. So these two terms is written for m is equal to n minus 1, and these two terms are written for m is equal to n plus 1, both for forward reactions, and similarly this is written for m is equal to n minus 1, and this is for n is equal to m is equal to n plus 1, and these are backward reaction and these are forward reactions. So now we have already defined all these coefficients here, so we can replace them here. Forward n minus 1 to n, n minus 1 to n. So if you see this, forward reaction can never take from n minus 1 to n, because it would mean the forward reaction is increasing the number of molecules of A. So this function actually is 0, because this is not allowed. Okay, so this will drop out as far as the forward reaction is concerned. And then here, when you are in n, and you can go to n minus 1, and that we have already defined here as k of n. So this is basically nothing but minus k of n times p of n comma t. Okay. Now here also only this n plus 1 to n is defined. This is defined, but this is not defined, because this is going from n to n plus 1 by forward reaction, not going to happen. So this is 0. So this term does not survive. And this one on the other hand is this k of n plus 1 p of n plus 1 comma t. Okay, so what we are saying is we identify all the intermediate states affecting the process, substitute all that, and then see which ones are actually going to survive and which ones are not. You could have directly written these two, because you know that forward reaction means being at n it will decay, being at n plus 1 it will get created. So this is easy to write intuitively also, but like I said before, it's probably a good idea to actually look at all the intermediate states and substitute and then do the details, and then you cancel out the terms which are not possible. So this is about the forward reactions. Similarly, if you look at the backward reaction, what is not possible and what is possible. A backward reaction can never decrease it, it can only increase it. So obviously this term is not going to be there, but this term is there. From n minus 1 you can come to n, and that is this term. Okay, so we can substitute that here, plus kb n naught minus n plus 1. So here again it cannot decrease by backward reaction, so this has to be 0, and you have one negative term, n to n plus 1, n to n plus 1, that is kb n naught minus n. So you got only these 4 terms. Okay, again you can apply the generating functions like this. Yeah, last 2 terms should be no, we still looking at the probability of finding n. Being at state n, the rate is dependent on only the number of molecules of B, because it's a backward reaction. Only for the forward reaction. Like I said, the first two terms are only describing the forward reaction. We are saying that the forward reaction, so similarly 2 terms for the backward reaction also. Yeah. The only difference between what you are saying and what we are doing here is, here we are identifying the system with number of molecules n. Okay. So in the phenomenological reaction rate equations, we only look at rate of change of the concentration backward and forward. Okay. But here our variables are different and we are identifying one molecule at a time. One molecule is changing the state. Okay. So therefore there will be 2 events. While you are at n, it can become n minus 1. So that is loss. When you are at n plus 1, by forward reaction you can go to n. So that is creation. Okay. So we are looking at all possible loss and gain of probability being at one state. Okay. So that's going to be a little different from the way that we did think about chemical reaction engineering. Okay. So we have a master equation. Then we apply the same generating function, and it's going to give you g of s comma t. Of course, the details of this will be shown later. I mean, it's given in the notes. You get a little complicated equation here. So we are writing the solution in terms of 2 variables, lambda, 2 parameters, lambda and k, and lambda is the ratios of the rate constants, and k here is the sum of the 2 constants. So now you will find the mean value . So the mean value itself changes with respect to time by this, and then if you want to look at the equilibrium, so this is an equilibrium reaction anyway. So if you look at equilibrium value, t time tending to infinity, so you will have this as n naught kb by kf by kb. And the variance of A at equilibrium, you can find this as n naught lambda by 1 plus lambda whole square. So how am I getting all these things? I am getting by looking at g, taking the derivative and then estimating its value at various values of s. Okay. The detailed derivation of this equation and then from here to here can be found in my notes. Okay, okay, we'll stop here.